Okay, this is section MA 259, section 7.1, and I wanted to work through a couple of problems here, starting with number 1. So we're given that we have this function f of t, and that's in a normal function f of t space, and we want to transform that to this capital F of s space through this Laplace transform. So we make this symbol, this capital fancy L, inside a bracket of f of t, so really this fancy bracket of t, and that's equal to the integral from 0 to infinity of e to the minus st times f of t dt. Okay, so since f of t in this case is equal to t, we end up with the integral from 0 to infinity e to the minus st times t dt. What I did first was use integration by parts to figure out what the antiderivative of e to the minus st times t of dt was. And so I made u equal to t, and I made dv equal to e to the minus st dt, and I found du, and that's equal to dt, and I found v, which is e to the minus st divided by minus s. So I plugged that in for u and v, and then minus the integral of v times du, and when I simplified that, I get this this antiderivative. So in this case, since we're trying to find the integral from 0 to infinity, the way to do that is to take the limit as p approaches infinity from 0 to p of e to the minus st times t dt equals, and then that's the limit as p approaches infinity, and then the antiderivative inside the fundamental theorem of calculus evaluated from p to 0. Or you should say from 0 to p, I suppose. Okay, so I applied p wherever I saw t, and I applied I applied 0 wherever I saw t, and this all simplifies to 1 over s squared. Now let's be careful about a couple of things here. So the first thing we have to be careful about is this s and this s. If p is approaching infinity and s is positive, then we have 1 over e to the sp. And as 1 over e to the sp, as p approaches infinity, I get effectively 1 over infinity if you say it crudely, and 1 over infinity as we say it crudely. That's not really the precise definition, but that crude way of saying it is 0. So we get 1 over s squared times 0, so this whole term becomes 0. No problem with that. Pretty easy to argue that. This one over here is much different, because I have this if s is positive, I have this e to the negative sp, which is 1 over sp. This part is approaching 0, no trouble with that. But this is infinity divided by s. And so you have infinity times 0. And we should remember from Calc 2 that whenever I see infinity times 0, I shouldn't just say, oh, that's 0, right? I need to be very, very cautious of that. This is an indeterminate form. So as it turns out, if I take the L'Hopital's rule of this first limit and take the derivative of both the top and bottom, I end up with the situation where it's easy to see that this whole term goes to 0. So I have 0 minus 0. And then from the second part, the fundamental theorem of calculus, when I minus and I put in this 0 here, I have 0 over s times 1, so all of this is 0. And I have 1 over s squared and times 1. So I have minus, and minus makes positive, and I'm left with 1 over s squared. And all of that's true if s is bigger than 0. If s was smaller than 0 or negative, then I would have e to the positive things and e to the positive things, and this limit wouldn't work out. So here's the thing. This pretty of t equals t, which has a constant rate of change, has a lot of work to it to apply a Laplace transform, but we were able to accomplish it, and when we accomplished it, we saw that the Laplace transform is 1 over s squared.